So we have to start with that numerator. So let's combine that. 5 minus 2 over x squared. Tell me what to do. Okay, so make that 5 over 1 and multiply by x squared on top and bottom, giving us 5x squared over x squared minus 2 over x squared. What's next? Perfect. We subtract the numerators. 5x squared minus 2 is 5x squared minus 2 all over x squared. So that's what the top of this becomes. On bottom, what do I have to do? Well, I don't have to multiply by 4x, but I can multiply, the common denominator is going to be 4x, right? So on the left, okay, I figured that's what you meant. On the left, we just have to multiply by x to get x squared over 4x. Plus, on the right, we have to multiply by 4 to get 12 over 4x. And when we add those, we're going to just get x squared plus 12 over 4x. Now this, remember, is division. 5x squared minus 2 over x squared divided by x squared plus 12 over 4x. What's our next step? Perfect. We leave the first fraction the same. When it becomes times, we take the reciprocal of the second fraction. So it's now 4x over x squared plus 12. And now there's some cross-canceling we can do. Can anybody tell me what I can cancel out here? Perfect. X squared and 4x can both be divided by x. X squared divided by x is just x. 4x divided by x is just 4. And that's going to become 4 times 5x squared minus 2 over x squared plus 12. Any questions? That is a lot of symbol manipulation, and as promised, we're going to pull back from that today and talk a little bit on a more practical level about equations and relations and functions, and actually working with more numbers instead of just variables and symbols like that. And as we reviewed yesterday a little bit, some of our forms of linear equations. And so I want to practice for a few minutes before we get into the relations and functions, talking about linear equations and writing linear equations from information given. You know, if we're asked to find the equation of a line through the points 0, 3, and 2, 6. Yes. Hopefully that's working. I'm not sure what's going on in my recording. Yeah, what do you need from the example here? Oh, I screwed something up there, didn't I? I forgot the x down there. Very good catch. Yes, I did overlook that. That denominator should be x times x squared plus 12. Okay, sorry about that. So now looking at forms of linear equations, find the equation of a line through 0, 3, and 2, 6. Now, in many cases, you might be given a problem like this, and it's left up to you to decide what form you would like to put it in. But let's say that we ask you to put it in slope-intercept form. For this information, it would have been probably easiest to use slope-intercept form anyway, so we're not really sacrificing anything by forcing you to use that form. So what we're given these 2 points, there's actually 2 pieces of information that we're being given here. First, you can find the slope. Remember, our slope formula is y2 minus y1 over x2 minus x1. So here that's going to be y2 is 6 minus y1 of 3. x2 is 2 minus x1 of 0. So 6 minus 3 is 3. 2 minus 0 is 2. So we have a slope of 3 over 2. The other piece of information that we're given here that's a little less obvious, a little more subtle, but you realize 0, 3, if I were graphing this, is a point on that y-axis. 0, 3 is our y-intercept. So now we can write this equation in slope-intercept form. It's just y equals slope times x plus the y-intercept. Well, here we have the slope is 3 over 2, so 3 over 2 times x. Our y-intercept is the 0, 3, so plus 3. And we've written our equation. Well, the intercept, remember, the y-intercept is where x equals, oops, what happened here? The y-intercept is always where x equals 0. So that's why 0, 3 gave us the y-intercept, is because it was x equals 0. Like I said, that one was kind of subtle because we had that, we snuck in that 0 for the x coordinate. Okay, so another example we might have, though, is find the equation of a line going through the point 6, negative 2 and perpendicular to a line through 7, negative 3 and, let's see here, 5, 0. Now there's a lot of points given here, but let's separate it out here. Find the equation of a line going through the point 6, negative 2. So that's the part that's defining the line that we're looking for. Well, what are the other 2 points for? Well, that line we're looking for is perpendicular to the line that goes through those 2 points. So the only reason we have these other 2 points is to find a slope. So I'm going to find a slope based off of those 2 points. So what goes into my slope formula from those 2 points? 0 minus a negative 3 over 5 minus 7. So 0 minus a negative 3 is plus a positive 3, or 3. 5 minus 7 is negative 2. So that's a negative 3/2 is the slope of the line through those points. The line we're trying to find, however, does it have the same slope as those points? It's going to be perpendicular to it, yes. And a perpendicular is opposite reciprocal. So the slope of our line, this is negative, our slope's going to be positive. Reciprocal, 3 over 2 becomes 2 over 3. That's going to be our slope. So our line is going to start out as y equals 2/3 x plus b. I didn't specifically state it here, but I'd requested slope-intercept form in the last equation. We're going to keep, or in the last problem, we'll keep going with that here for this example. How do we find point B, or what B is, the y-intercept? That's where this point comes into play. Since it wasn't 0 for x, we can't just take the y-coordinate as our y-intercept, but we can still use that point to find our y-intercept by putting in, since it is 6, negative 2, we can put negative 2 in for y and 6 in for x. And we'll solve for that y-intercept. 2/3 times 6 is 4. And we solve for b by subtracting 4. So b, the y-intercept, is at negative 6. So y equals 2/3 x minus 6 is that equation in slope-intercept form. We also had point-slope form. Recall point-slope form was y minus y1 equals the slope times x minus x1. Basically what this is it is shifting or transforming the location, translating the location of the origin. It's taking the origin to that point x1, y1. Then when we look at graphing other functions next week, we're going to use that similar type of translation to come up with a graph of other functions. But if they go through a given point, a known point. So anyway, let's look at find the equation in point-slope form. Of a line through 4, 9, and parallel to a line through 5, negative 6, and 3, 1. So once again, this part up here is describing the line we're looking for. This part down here is describing another line that we're using to get it. What part do we really want about that line? All we care about is, again, the slope between these 2 points. So to find the slope, it's going to be what? 1 minus negative 6 over 3 minus 5. 1 minus negative 6 is 1 plus 6, or 7. 3 minus 5 is 2. So 7 over 2 is our slope. Parallel. So what's going to be the slope of our line? 7 over 2. So our equation with a slope of 7 over 2 is y minus, the y coordinate of our point here is 9, so y minus 9 equals our slope, 7 over 2, or 7 halves, times x minus x1, which would be 4. There's our equation. Ah, yes, that should be a negative 2 down here, shouldn't it? So yes, negative 7 halves. I've been off all morning, so I'm sorry. Please feel free to jump in if I make stupid mistakes like that. So yes, that is a negative 7 halves for the slope. Well, let's look at a different problem. Let's say Pat starts 60 miles from home. Riding bike towards home. After 3 hours, oops, let's get this right. Yeah, so after 3 hours, Pat is 24 miles from home. Find the total time for Pat to get home. So what we have here is we have 2 coordinates. Pat starts out 60 miles from home. That's time equals 0, distance equals 60. After 3 hours, Pat is 24 miles from home. So that's time equals 3, distance is 24. We can find an equation from that. First, we're going to find our slope. Well, 24 minus 60 over 3 minus 0. 24 minus 60 is negative 36. 3 minus 0 is 3. That's a slope of negative 12. So Pat is traveling at an average of 12 miles per hour towards home. His distance, the negative means the distance is getting smaller. We could write an equation here in slope-intercept form rather easily. Slope of negative 12, so it's negative 12 times x. How are we going to find our y-intercept? Normally we'd do plus b and we'd take one of the points and put it in there to find b, but in this case the y-intercept has to be what? 60, perfect. This is 0, 60. When the x coordinate equals 0, that's the definition of the y-intercept. So the y-intercept is at 0, 60, or the y-coordinate of 60. So y equals negative 12x plus 60. What we wanted to know is how much time is it going to take for Pat to get home? The total time. Well, when Pat is home, Pat's distance from home will be 0. So y will be 0. So we have to solve for x, which will be the time at which that occurs. Now it's just solving the equation, subtracting 60 to get negative 60 equals negative 12x. And divide by negative 12. So 5 equals x. So Pat will be home at 5 hours. Any questions there? Okay, well these equations we've talked about are linear equations. And linear relationship, is one form of something called a relation. A relation is just anything that takes one set of numbers and somehow connects it to a second set of numbers. There are several ways of expressing a relationship. One of the simplest ones is something called a mapping. A mapping just takes a list of all numbers that we can start out with, that first set of numbers. Let's just put numbers in here. Maybe it's negative 3, 0, 5, 12. That's our first set of numbers. Let's take our second set of numbers. And let's say this is negative 9, negative 1, 2, 7, 20. And the mapping tells us that negative 3 is going to become 2. 0 becomes negative 9 or positive 7. 5 becomes negative 1 and 12 becomes 20. This first set of numbers is usually referred to as the domain. That's the set of numbers we start with. That domain is then converted through this relation, into something called the range. That's the second set. That's the set of numbers we end up with. Well, another way of expressing this relation would be simply a table. We could list out all these pairs up here, all these relations up here, by saying we've got the domain. The domain, by the way, is usually represented with the variable x. And the range, again, usually represented by the variable y. And this says negative 3 becomes 2. 0 becomes negative 9 or 7. So we'd have to have 2 entries in here for that. 0, negative 9, and 0, 7. 5 becomes negative 1. And 12 becomes 20. Yes, I just randomly picked numbers and threw them in. So that is a second way we could have expressed that relation. A third way we could have expressed the relation. If we can express them in a table, we can express them as ordered pairs. I could have just done 3, 2. 0 became negative 9. 0 became 7. 5 becomes negative 1. 12 becomes 20. Fourth way is I can express them on a graph. It can either be as points or a curve. Now, when I say the word curve, I don't necessarily mean it has to be curvy. A line is a curve. It's a straight curve, is all it is. This relation that we happen to put up here might be a little hard to express on the graph, but we've got 3 becomes 2. 3 becomes 2 would be right in there. 0 becomes negative 9, and 0 becomes 7. So 0 becomes negative 9, 0 becomes positive 7. 5 becomes negative 1, and 12 becomes 20. Those are the points. Something like that. These are points, not a curve, because I can't draw a curve through those. Now, since there are points, this relation can't be described with our fifth method, which is an equation. There is no equation describing these points. But we've looked at equations like, y equals 3x minus 7. And you can see from that how that can generate these other forms. X represents the domain. That's the values we start with. And y represents the range. That's the values we end up with. And we've made tables when we started out graphing before we came up with shortcuts. We made tables based off of that equation, where we picked values of x and we calculated what y had to be from that equation. And we graphed those tables on the line. So we have seen these forms of relations before. Well, the focus of this part of the class, though, is not just on generic relations, but on a special type of relation called functions. The technical definition of a function: every value in the domain goes to exactly one value in the range. So to start illustrating this, I'm going to use mappings at first. So I've got my domain and my range. Is that a function? Yes, it is. Every value in the domain goes to exactly one value in the range. Is this a function? It is. Every value in the domain, every one of these values here in the domain, goes to exactly one value in the range. It doesn't say anything about the range values getting exactly one value. The 8 here doesn't get a value from the domain, but it doesn't matter. It's only the values of the domain. I might have this. Is that a function? Does every value in the domain go to exactly one value in the range? Yes, it does. Is that a function? It is not, because the 3 in the domain goes to 2 different values in the range. So that's not a function. Now, there are some special names for these different types of functions. These 3 here are all functions. There's a term called onto. Onto means every value in the range gets at least one value from the domain. I used very sloppy wording there, but what that means is every value in the range has at least one value in the domain that gets mapped to it, that becomes it through that relation. This is onto. The 3 here has at least one value. There's 3 different values that become 3, but there's at least one that gets mapped to the 3. This is also onto, because every value in that range has one value from the domain that comes to it. One-to-one means that every value in the range gets only one value from the domain. Only one of these is one-to-one. That's this one. Every value in the range had exactly one value in the domain that came to it. These things are not necessarily important to us at the beginning of all this, but at some point we're going to talk about something called an inverse of a function. That's how we reverse a function and make it go backwards. And to have an inverse, a function must be both one-to-one and onto. So we've looked at the mappings, and we can tell from the mappings which ones are functions. You know, these first 3 are functions. That last one is not. Let's look at our other forms. If I have a table, I'll make this a little smaller. Is that a function? It is. Every value in the domain, every x value, goes to exactly one y value. Is this a function? No, why not? Yeah, negative 2 becomes 5. Negative 2 also becomes 3. So that is not a function. We can use a similar strategy for ordered pairs. Is that a function? Yes, it is. Every value in the domain is unique and it goes to one value in the range. Is that a function? Yes, it is. Every value in the domain is unique and it goes to one value in the range. Now they all go to the same value. It's definitely not one-to-one because all of them go to that same value of 1 in the range, but it's still a function. Is that a function? No. Negative 2 goes to 4 and negative 2 also goes to 0. That is not a function. Let's look at a graph. If I put points on the graph, now I should note here that those line up. Is that a function? No. The domain, remember, is the x values. That's the x-axis. The range is the y values. Here, this value in the domain goes to two different values in the range. That's not a function. When we're dealing with a graph, there is a shortcut for telling if it is a function. It's called a vertical line test. When I look at a graph, even if it's not just points, it might be a curve. Is that a function? It is. And the way we tell is if I take a vertical line and I slide it across that graph, is there ever a spot where that line crosses the graph more than once? No. As I slide it across, that vertical line never touches the graph in more than one point. Come on now. So, Get my color to set. There we go. We might have a graph that looks like this. Is that a function? No, it is not. Because a vertical line right here actually crosses the graph in 3 points. It's more than 1 point. Crosses it here, here, and here. So that is not a function. For an equation, it's much simpler. Now I'm just going to use the variables x and y, where x implies domain, y implies range. X has a power of 1. Y has a power is a whole number. So what does that mean? Oops, I screwed those up. Sorry. It's really been one of those days. I apologize. It's not x that has a power of 1. It's y that has a power of 1. X has the power of a whole number. I'll pause for you to get a chance to change those. So y equals 7x to the 8th minus 2x to the 5th plus 39x to the 4th minus 2x plus 473. Is that a function? Yes, that is a function. Because y has a power of 1, and all the powers on my x are whole numbers. Is this a function? Technically, no. You might be like, well, isn't that y has a power of 1 and doesn't x have a power of 1? No, when I have dividing by x like that, that's implying x is the power of negative 1. That's not a whole number, that's an integer. It's a negative number. Now we can define the domain and range of a function like that to make it a function in some cases. We would restrict the domain. As long as x is not equal to 1, then that is a function. We'll talk about that more later. How about y equals the square root of x plus 6? Remember, square root is really a power of 1/2. So that is not a function. That is not a whole number power on x. Now, once again, we can define it in such a way to make it a function. You remember a square root, if we put in a value for x here, let's say we put in the value of 3. Well, 3 plus 6 would be 9. Well, the square root of 9 would be positive 3 or negative 3. We're getting out two different values, so therefore it's not a function, right? But if we defined it in such a way that it was only the positive results of that square root, then it is a function. Then there is only one outcome. So like I said, the same with this one here. There are cases where we can restrict that relation, and then it does become a function if we make those restrictions. We are used to seeing equations written like this, y equals 2x plus 3. But when it's a function, we often use a special notation. What is the difference between y equals 2x plus 3 and this is pronounced f of x equals 2x plus 3? Absolutely nothing. They mean the same thing. This notation here is simply telling us that that is a function, that we've defined it in such a way that it is a function. The notation f of x, now it could use other letters. We could use g of x or h of x or whatever. That way we can refer to the functions as f, g, and h. So that's one of the purposes of using that notation, is that we can refer to the functions very quickly. This is the function f or the function g or the function h. One of the other things it does is it allows us to ask a question. If f of x is 2x plus 3, we might ask, what's f of 5? What that's asking us to do is to evaluate this function up here, replacing x with 5. So f of 5 is simply 2x becomes 2 times 5 plus 3, or 13. So that is just saying this function evaluated for the value of x being 5. Now we can be a little trickier than that. We might ask you, what is f of x minus 4? Well, remember, f of x is 2x plus 3. F of x minus 4 is asking us to replace x with what? X minus 4. So instead of 2 times x, this is 2 times x minus 4 plus 3. And of course, we could do some simplifying there. Distributing the x, you got 2x minus 8 plus 3 gives you 2x minus 5. So f of x minus 4 is 2x minus 5. So if I say f of x equals 3x plus 1, and g of x is, or 3x squared plus 1, g of x is 5x minus 7. I might ask you, what is f of 5? How would I find that? Yeah, 3 times x squared becomes 5 squared plus 1. And if we evaluate that, yes, it's 3 times 25 plus 1, which is 75 plus 1, otherwise known as 76. What if I ask you for g of negative 3? How am I going to do that? Yeah, we replace x here with negative 3. That's 5 times negative 3 minus 7. 5 times negative 3 is negative 15. Minus 7 is negative 22. G of negative 3 is negative 22. F of 5 is 76. Well, what if I step it up a bit and I ask, what is f of x minus 2? Well, I'm going to replace x with x minus 2. So 3 times x squared becomes 3 times x minus 2 squared plus 1. X minus 2 squared, x squared minus 4x plus 4. If we multiplied that all out, x minus 2 times x minus 2. Of course, we still have the plus 1. We will distribute the 3, giving us 3x squared minus 12x plus 12, and still plus 1. And finally, we'll combine the like terms. That's 3x squared minus 12x plus 13. That is f of x minus 2. What if I wanted to know g of x plus 1? Well, g of x was 5x minus 7. So this is 5 times x minus 1 minus 7. And we just do out the algebra from there. 5 times x minus 1, of course, is 5x minus 5. Minus 7, well, we combine. That's 5x minus 12. That is g of x. That should be a plus 1, thank you. So that should be 5x minus 2, not minus 12. Let's make this interesting. I'm just going to rewrite these so we have them. So those are our functions. I want to make sure I've got them right. I do. What would be f of g of x? What that's saying is 3x squared. I'm going to replace x with g of x, which is 5x minus 7 squared plus 1. Five x minus 7 squared is 25x squared minus 70x plus 49. And then plus 1 is still sitting out there. If you remember our perfect square trinomials, this isn't so bad to do. Remember, it's just the first term squared, so 5x squared gave me the 25x squared. Then it's you multiply the terms together. 5x times negative 7 is negative 35x. You double that is negative 70x. And then the last term squared, negative 7 squared, is the positive 49. We'll multiply the 3, distribute the 3. 75x squared minus 210x plus 147 plus 1. And of course, we just combine the 1 in with that. 75x squared minus 210x plus 148. At this point, you can probably guess what's going to come next. In your notes, I'm going to ask you to find g of f of x. I'll give you a few minutes, and then we'll go. So we'll replace x with f of x, which is 3x squared plus 1. We distribute the 5 to get 15x squared plus 5. And we subtract the 7. 15x squared minus 2. That is g of f of x. For right now, that's where we're going to leave this at. I know we're a few minutes early, but I think that's enough material. The function notation and the idea of a function takes a while to get used to. So I'm going to leave it at that. Homework 9C covers the material that we discussed today. Remember also, by the end of the day Monday, quiz 9 is going to be due. So if you get through the homeworks and you're doing fine, get the quiz done as well. Remember, next week is week 10. The first day of the following week, week 11, is our test. So that is April 8th, I believe, is test 2. So make sure there is a review sheet posted out there for that test. Make sure you're looking that over to see if you remember the stuff from spring break, from before spring break, so that we're ready for that. Okay, you guys have a great day. We'll see you next Monday.